candidate at Toronto Metropolitan University and Ghent University. And before we start our session today, I'll give the floor to Saba, the co-chair of the Modeling and Integrated Assessment Specialist Group, to give us an introduction about the group, and then we can start introducing our speakers. Saba?
Yeah, just go down a little bit. Try to click. Yeah.
Yeah. Okay. So the voice is going to.
Yeah.
Thank you, welcome everyone to the first session of this newly started initiative, the MIA Academy. So my name is Saba, and I'm a vice chair of Modeling and Integrated Assessment Working Group, Specialist Group at the IWA. Yeah. On behalf of Elena Torfs, who is the current chair of the Modeling and Integrated Assessment Specialist Group, I'm going to give you a very brief introduction to the group and what we are and what we do before the start of this session. So MIA, Modeling and Integrated Assessment, is one of the 50 specialist group at IWA, and it's also one of the most active ones. So we have quite a large management committee, and we are quite active in the IWA at the conferences, at the different organizing webinars and in different ways, let's say. The main idea of this specialist group is to gather people from academia, from industry, from utilities, from everywhere that are working on modeling and optimization and assessment of water systems in general. So not specifically to a particular part of the water system like wastewater or drinking water, but every aspect that can relate to the water cycle and modeling and improvement of those systems. So as you see on the right-hand side of this figure, we have quite also an active page on IWA Connect Plus and a website also that you can go and check and find the information about the things that we do. And also the other members, of course, of the management committee. But to give you some brief, let's say, overview of the main activities that we have. So at the MIA, we have some task groups and working groups. Task groups are usually a gathering of a few people, let's say, that are working to perform a specific task in a short, let's say, relatively short period of time, 3-4 years. And at the end, they publish a scientific and technical report, like the ones that you see on the bottom, for example, for the physiochemical modeling, CFD, greenhouse gas emissions. These are the ones that are recently published, and they are almost all of them. I think the CFD is also available open access. So you can download them from the IWA publishing website. And you see the list of, so the working groups are a bit different. So they are a bit longer, more people are involved, and they are not necessarily, let's say, doing a specific task, but they are working on that area in general. So we have hybrid modeling, for example, the most recent one that is started, let's say, a couple of years ago. And also the conferences. So I think there is more information on the next slide on that, so we'll talk about that later. But yeah, as I said, also we have a YouTube channel that's all the webinars, for example, that we are organizing, and also these sessions will be recorded and they will be available there for you if you want to watch later, or give the link to somebody that couldn't join these sessions to watch. So for the conferences, indeed, so we have two main modeling conferences: Water Resource Recovery Modeling Seminar and Water Matrix, so the Symposium on Modeling and Integrated Assessment, which are the main two conferences in this area of water modeling that we are supporting as MIA, and the whole management committee is behind this in terms of helping the people, organizers, and people that are involved in organizing those conferences. The next one is coming up next year in June in Barcelona. So the next WR mod, and the next water metrics will be in 2027 in the south of France. So for all of you are invited to join those conferences if you can. That was it. So a very brief introduction about the main things that we do at MIA. And as I said, so we are quite active in the IWA Connect Plus, our websites and our LinkedIn page. And you can check those places to get more information about all the people that are involved in helping this specialist group to move forward, and more information on that. So I will give the give it back to you, maybe to Amber, or maybe other people that are going to talk about this session. So have fun, and I hope that you enjoy this.
Thank you, Saba. So a bit of introduction on the MIA Academy. It started as an initiative from the young water professionals in the group, for young water professionals who might think that modeling is a cryptic language, and we wanted to demystify that during doing a series of sessions. So we have a session every month, and these sessions are going to be recorded and uploaded to our page with the resources that you can use for further reading. The first block is going to be focused on wastewater. So the sessions are, this session is about what are models and how can they be useful. We'll introduce next activated sludge models, sedimentation models, physical chemical models, data handling and model calibration, validation and evaluation. And we'll also do anaerobic digestion modeling at the end of it all. So the goal here is to not just provide knowledge that is of the highest quality, but it's also accessible to everyone. So all you need is internet access and a couple of hours of your time, and you should be able to follow through. And by this, I'll give the floor to Luz to introduce our speakers.
Okay, so I get the honor of introducing our speakers. So firstly, we have Bruce Johnson, who is going to be presenting today. He's a professional engineer and board certified environmental engineer and an Iowa fellow. Bruce currently works at Jacobs as a senior technology fellow, and he is a wastewater process engineer that has been promoting the use of simulations throughout his whole career. And I think with 37 years of experience, he's going to bring a lot of interesting insights to this session. And then next, we also have Jean-David Therrien. So Jean-David currently finished his PhD at Université Laval at Modelo. His PhD was about the wastewater data pipeline, and right now he's doing a postdoc at Ghent University at Biomed. He's working at the Water Frame project, and he's creating a set of standards to share and reason about water reuse. And the overall theme of his work has always been on improving data processes to make better decisions. And I'm now gonna give the floor to you.
All right, thank you, Luz. Thank you, everybody, for giving me the opportunity to speak with you today. I'm very excited about this session, so let's just get started. So here we go. Before we dive in, it's worth asking why anyone should care about models. Right? It's very obscure. Why do we care? And I hate to break it to you, maybe it comes as news, but you are modeling at this very moment. And that is why you should probably care about models. And what do I mean by that? Let's zoom way out just for a second. We're engineers. What are we doing? What we're trying to do as engineers, roughly put, is to understand the forces of the natural world and harness them somehow to try to solve a problem or improve a situation, whether it's public health, public safety, reducing costs, and so on. But if you're going to act on the world in that way, you first have to know what's in it, right? So your understanding of the world is very important. And we see the way we interact with it is seemingly it's through like our consciousness. So we are aware of the world through our senses. And it's like there's this direct highway between the real world that we want to change and what's going on in our head. But that is actually not how it works, right? Because the skull has no windows. There is no connection between the outside and the inside. All you have is electrical signals in there. So whenever you interact with the world, the brain receives an electrical signal. It has to guess what it means, and then it needs to present it to the consciousness in a way that will help you somehow, probably enhance your chances of survival. There's no guarantee that the most helpful thing is the truest thing. But either way, the brain will present to your consciousness a model. So no matter what you do every second of every day, you're dealing with a model with all of the flaws that come with that. And one of the flaws is that models oversimplify, or they make or they make mistakes sometimes. Well, yeah. Hello, now you can see me in the little window as well. So yeah, so the brain will prefer useful lies to over the real sometimes. So here we have this like famous optical illusion, for instance, where you have a checkerboard, and I don't know about you, but to me it really looks like square B is brighter than square A. Like I can't make myself not see it that way. And yet, if I take a solid block of color here, of solid gray, and I slide it over squares A and B, I see that they are, in fact, the same color. So there's this effect that the brain produces because it knows about shadows. It has a model of how shadows behave and how colors in the real world behaves, and it knows that if something is in the shadow, it should be brighter when it's not. So it will overcompensate and present to me a bright color. So I'm stuck, and as humans, we are stuck in this way of perceiving the world that is filtered. And that means that you have to rely on your senses, but you can't fully trust them. And another way in which you can't really trust them is that they don't cover the full real. So here we have the metaphor of the six blind men and an elephant. And depending on which part of the elephant they touch, they might think that an elephant is actually like a rope or like a snake or like a carpet if they touch the big ears. So you need more sophisticated tools or something stronger than your senses to really fully apprehend the real. Another thing to consider is that even if you did have full access to the real, it's just too big for your minds, right? Like you have the skin of an elephant is in plain view. You look at it, you see it all. But if you were going to see everything that is real about it, it would be way too much, and your brain would just give up halfway. There's just too much down there. So in the end, you don't have access to the real that you're trying to influence. Now what? What do we do about this situation? And that's where models come to the rescue, right? So we have this very powerful tool that comes with modeling that is abstraction. So it's reducing reality to only its relevant features. And that allows us to take a very complex situation like individual elephants in all of their complexity. Here I'm talking about elephants. Assume I'm talking about water or anything that interests you. I like elephants. It's fine. So you take these individual ones and you abstract away the common features, and you end up with those characteristics that you can assign to the class of elephants in general. You move away from real objects with all their messy complexity into a sign that fits comfortably in your head. So simple models and abstractions like that support understanding. And I wanted to bring up this quote attributed to Albert Einstein, but who the hell knows, because people attribute Albert Einstein all kinds of things. So in appearance, he said, everything must be made as simple as possible, but no simpler. So by that, I think what we mean is that a simple model should support understanding, so only describe the things that matter, so we're not confused, but not be overly simplistic, where you hide away inconvenient complexity that is still important to what you're trying to understand. So a very famous example of that is the spherical cow in physics, the spherical cow of equal density throughout, which might be enough to discuss gravity, but probably not to discuss milk production. Another tool that we have in the same vein of abstraction is to organize the world into systems. So a system is just a group of things out there that when they're put together, they achieve a function or a purpose. Yes, so a system allows you to understand the causal relationships between things. You have elements, and because of the way that they affect each other, you end up with a specific result that gives you a system which can be connected to another system to make a larger one. And that way of reasoning leads you to see the world as basically complex objects that contain smaller parts that affect each other and that have inputs and outputs. And that is the way that we usually define models as well. It allows us to create chains of causality. So because I do A to object X, the response of object Y will be B. I can make that story. And I just want to draw attention to what I just did here. I made a sentence that explains a relationship. And that is, so that is pointing to the fact that speech is itself a conceptual model. When I use words and I transmit them over the airwaves and over the interwebs and over the speakers in your computers, I create images in your mind that used to be in mine. It's possible that the details of the image in my mind is different from yours, but still there is that transmission of an abstraction. So speech is another way of creating models, is a model itself. Another very useful category of models is the heuristic. So that's a heuristic is a rule of thumb that applies to a category of situations. It's when you tell yourself, oh, when the sky is this shade of gray, I bring an umbrella. So it doesn't have to be true all the time that shade of gray leads to it raining, but it's good enough because it prepares you in case of rain, and that was the task. So it's very fast. There's no mechanism needed. You don't need to think about why it rains, but it will get you to do the thing. Except it's prone to errors. Before we had the optical illusion, it's your brain making a heuristic, and the brain got fooled by the situation. So more deliberate reasoning will help you avoid those types of mistakes. And there are other types of models that help us do that. If you're more interested in how heuristics work and how they can lead us astray, there's this great popular science book, Thinking Fast and Slow from Daniel Kahneman, that I highly recommend. So what's a model then? It's any representation of a system. So to me, an Excel spreadsheet is a model. A design report is a model, a CAD drawing is a model, and a conversation you're having can also be a model. So these are all different ways that you represent reality and the cause and effect relationships that you see in it. And different types of models will have different utilities and different levels of fidelity as well. So why should you model, or rather, why do you already model? Right? So the main things, you simplify a very complex reality into its essential components. That allows you to do that. It allows you to reason about your system or the thing you're interested about. You can explain it, and you can also, once you have that story, that understanding, predict the behavior of your system. And also very important in the engineering profession is that it makes your thought process explicit to your stakeholders or other people you're interacting with. If you specify your model, other people can look at the model and hold it in their head in the same way that you were able to hold it in their head, instead of having to each be a blind man on the elephant. Now you might be asking yourself, wait, I thought there would be math. This is a modeling MIA Academy thing. Where's the math? And if you're joining us from the UK, you might be asking, wait, I thought there would be maths. In either case, no problem. I can hook you up. Here's some math. So mathematical models is just another type of model in my view of it. But it is a special one because it's also a discovery engine. So mathematics is really valuable as special because it forces you to define things using really unambiguous concepts, or to really state what you mean when you use a symbol or another. And that specificity allows you to generate new truths that you might not have known when you started defining your system. So here we have a very trivial example of the root of two, the square root of 2 is defined as the number that when multiplied by itself gives 2. And then you apply some mathematical reasoning to it. You only started knowing that definition, but at the end of that reasoning, you end up with this new fact that you didn't know before, that the root of 2 has to be an irrational number. So a number that has decimal numbers that go on to infinity. So you were able to discover by stating things very unambiguously. In the sciences, that is hugely helpful because it allows us to model patterns of nature, not only describe them, but discover new ones and probe our understanding of existing, currently known laws of nature. And on the other side of the aisle, in engineering, you use the patterns that have been discovered to our benefit, to design, control, predict, and make rational decisions. So hugely important. But before we get into the specifics, it's nice to think about the fact that we have created this sort of language, sort of formal way of doing things that leads us to understand the natural world. There's this philosopher from the 1960s, Eugene Wigner, that reflected that the enormous usefulness of mathematics and the natural sciences is something bordering on the mysterious and that there's no rational explanation for it. There's no reason why a way to use language will lead us to truth. And then he adds, it's a wonderful gift that we neither understand nor deserve, and we should be grateful for it. So I hope you finish this seminar as grateful about this as I am. So when we think about models, what are the parts of it? Let's think of it as a system. So what's going into it? You put into your model the data that you've got, the assumptions that you have about how the system you're modeling should work and what phenomenon should be important. And then the purpose or the objective that you have doing the modeling, it also goes into it. You squeeze all that real nice, and you end up with this one artifact, which is the model, like this piece of software. And inside of it, you will see these pieces, the inputs, the outputs, of course, and then inside the model itself, parameters, and then the variables, which represent the state. And we'll go through like what each of those mean. First of all, let's have a little bit of a look at the data, right? The data is the model's point of contact with the real world. That's how you check that whatever it is you're computing actually fits some sense of reality. So you use data not only like as an input, but also to determine the model structure, because you build models based on on data that you have. Otherwise, it's not useful. You use the data to calibrate parameters, and we'll go further into what parameters are later. And you can use different sets of data to validate a model's predictive power. So does it work equally well with this data set versus another? Or you can use it to set initial conditions before the model starts running. You collect them all kinds of ways, and all ways are equally good and interesting for different purposes, sensors, lab assays, field observations. You get it from the weather service online, all kinds of things. But no matter where you take it, you have to be aware that there's going to be a list of steps that you will have to go through with your data before you can actually start modeling. That will probably be the topic of another MIA Academy session, but just for now, let's go through them. So you will run around all kinds of places, ask all kinds of people for the data that they have and that you need. You will gather it together somehow, and it'll look all different, and you will need to compile it in a way that makes sense to you, that you can start working with. And then you extract the data and make it maybe into a table or something neat that you can use during the modeling exercise. Then you look at the data that you have there and you clean it, because you can't immediately trust that it was collected correctly and that there are no errors in it. So you go to work and you clean it. Once you've cleaned, you can do some data mining, see what variables seem important, see which ones are good quality to determine what kinds of model you can do with them. It will transform them so they have the right frequency, so that they're all behaving nice in the right format for the modeling software you're using. And then finally, you can split it into a data set for calibrating, a data set for validating, and possibly a data set for using, or you'll compile that later. So this is where the actual modeling starts, right? Like everything in that dashed area is what we typically think of as modeling, where you will first go through the calibration phase, where you'll try to match the model's behavior to the data that you've observed by tuning parameters. And then you show it another bit of data that the model hasn't seen yet to be sure that it's still fitting the observed behavior, even though like that data wasn't seen while tuning the parameters. And then finally, when you're satisfied that you're actually representing in a model the thing that you want to represent, you start using it. What's important here is that every bit of that pipeline, and no matter where you are in the pipeline, everything that's on the left of where you are, if it's not done correctly, it's going to cause you trouble. It's going to cast doubt on the quality of what you can do on the right side, because it is like a sequential set of steps. So that leads us to the theorem, the law of conservation of garbage, right? So we often hear the expression said as garbage in, garbage out. If you put bad quality data into your model, even if you do a great job calibrating it and designing it, it's going to still give results that don't help you model reality. And the corollary of that is you have good data, most likely you'll have a good model. So here I pulled a quote from Mr. Charles Babbage, who is the inventor of the first mechanical computer, right? And even then, he says that people were asking him, Mr. Babbage, if I put the wrong figures, the wrong data into the machine, will the right answers come out? And he responded saying, I'm not able to even understand the kind of confusion of ideas that could provoke a question like this. So like it's beyond his understanding. So don't make Charles Babbage sad. Check your data. Don't expect bad data to give a good model. And that's the moral of the story here. So common issues that you might have with data is, first of all, it's fragmented. So it's coming from all kinds of different sources. Each have their different way of collecting data and organizing it. So it might be difficult to put together in a nice, convenient package for your modeling exercise. Also, some of it might just be unavailable. Maybe you have a certain type of model you wanted to use, but the thing that was supposed to be measured wasn't, or the data got lost, and you have to be inventive to sort of recreate a simulacrum of the data that you wanted, or something like that. Or it might just be of dubious quality. Sensors, wastewater sensors, for instance, are in wastewater, so they get really dirty really fast, and it's not because you have data collected from a sensor that you can trust it. Faults can happen. In labs, errors happen. You can make mistakes sampling, or you think your sensor is in a place, but it's in another. And in all cases, if you had enough context around your data, enough information, maybe you could go back and think and understand where the error happened and sort of somehow fix it on the back end. But sometimes you don't have that context. So what I want you to take home with you today is like always be critical of your data. Is the foundation of your modeling exercise, and many things could go wrong with it. And let's talk about the roles of data inside a model, right? We mentioned all these three things before: the inputs, the state, and the output. So the inputs is just typically a thing you can measure, right? Data that you have from the real world, and you will feed it to the model so it can initiate its calculations. Whereas the state is also data, but it's data that is internal to the model. It's kind of bookkeeping. So as you suppose that you have a model of an activated sludge tank with bacteria in it consuming the carbon coming in, right? So what you might be able to measure and put in the inputs is whatever is the concentration of carbon in the influent to that tank. But inside the tank, there's bacteria consuming it. You have to have a number in your model that represents how much bacteria is in there. But it's hard to measure bacteria. You may not have that number. No matter what, the model will produce a number for its internal bookkeeping. So that's the state. And then finally, the output, that's just one of the variables that the state that the state contains, but it's one of them that is of interest to you as the modeler, right? And that is often another measurable quantity because you will want to confirm that the model's outputs or its states match with the reality. So often what you consider the output is something that you've seen out there. And then finally, the parameters, they came up a few times already. So what they are constant values contained in the model's mathematical form. And what they do, their purpose is to turn the equation, which is at the beginning a general description of the system you're trying to describe, into the equation that describes your exact system. So what do I mean by that? Here we have the Monod equation, and the growth rate of bacteria is represented by the maximum possible growth rate of that bacteria times the amount of food it has divided by a sum of the food it has plus the amount of food at which its growth rate is half of the max growth rate. It's a bit of a mouthful. You don't need to really necessarily understand the Monod equation, but what matters here is you have two parameters, right? You have mu max, so the maximum growth rate of that bacteria population, and Ks, which is like I said, the amount of food at which mu is mu max divided by 2. So two parameters. Here, this graph that I'm showing in blue, that's the Monod curve. So for different amounts of substrate, this is on the x-axis, you have the amount of growth on the y-axis. And as I run this, you see if I change mu max, I will change the overall height of the curve. And if I change Ks, I change the squishiness of the curve. And then the process of calibrating those parameters would be to choose the values that ensure the best fit between that blue line and the red dots, which are the ones that I've measured, right? So after having done that calibration, I end up with the equation with the numbers that really represent how my system was behaving. So that's what parameters do. And this process of finding the best parameters, that's called calibration. And now outputs. I mentioned outputs before. I said they're a kind of data that the model puts out, like either state variables or output variables. But then another kind of output that you should realize is there is the model itself. You created this artifact that is now reusable, can be interrogated, it can be used in all kinds of ways. And also, as you were building that model, you created understanding inside your own mind. And that's another output of the modeling exercise that's hugely valuable. One thing to keep in mind is whenever you do a modeling exercise, you should make sure ahead of time that the outputs that it produces fit the purpose that you had going in. Otherwise, the whole exercise is kind of pointless. So, if you wanted a model that simplifies a complex process, you might be okay with a small model that has a few parameters and a few equations and can quickly be explained. Whereas a very, very accurate model that would be really complex, very precise but complex, would not fit that purpose of explaining. So it all depends on what you want to do. So that was my general view of mathematical models. But now what we can do is enter and have a quick look inside the zoo of all the different kinds of models that exist in that category of mathematical models. And there's no one way to really split them along the different properties and categories. Like I wish I could show you like a three-dimensional like graph and place models here and there and be like, oh, they go this way and that way. But instead, we're going to have to go through different properties and be like, okay, there exists either the models exist in one side of that category or another, or they're somewhere along the spectrum. So we're just going to go through a few of those right now. The first of which is like more or less a dichotomy. It's whether it's static and dynamic models. Static models, what that means is that the model will take in constant inputs. So inputs that don't change with time. So that allows you to see what the state of the system will be at equilibrium. And that can often be solved analytically, like with algebra, rather than going full on numeric, although not always. And then dynamic models are those that accept inputs that vary over time. And when that happens, what you can do is compute the new state based on the new data coming in at every time step. And that shows you sort of a simulation of how the real system will change over time given those inputs. And that is often solved numerically. Another way of describing models is whether they're lumped or distributed. So what it means is here we have different like levels of lumpedness or distributedness. So here's the CSTR, constantly stirred tank reactor, thank you, where the way it works is the state is assumed to be exactly the same everywhere inside that reactor. However, we still allow the state to evolve in time, right? So when you talk about chemistry in a mixed tank, that's usually plenty. However, if you're thinking about settling, well, it would make sense to have a model that at least the state varies based on the depth, because you want the top to be clarified and the bottom to have sludge. So you have this distribution along the depth axis. You still evolve in time. That is still there. And finally, you have 3D CFD models. That is a model where the state is allowed to vary in all directions, as well as in time. And that could be used, say, in a chemical reactor where you're supposed to have good mixing, but you think you're not having it. So you want to model like where the water goes and there are dead zones in it or whatever. So there you go. Another very critical axis, and we'll spend some time on that one, is the first principles versus empirical axis. Here in first principles, what that means is that you start your modeling process from fundamental laws. So for instance, in the case of our skier over here, the fundamental law is Newton's laws of motion and also the existence of gravity and like the geometry of the slope, right? And then you apply that to a system at hand. So you do your free body diagram. You're like, okay, according to the fact that those forces exist, here's how they should play out. You enter initial conditions. So you say, well, how much is the friction? At what speed am I going at time zero? And once you've set all these things, you can just let the mechanism unwind, because the laws tell you what change should happen, how the system is supposed to evolve. So that is a very common type of model, and we'll talk more about it later. One example is computational fluid dynamics. That's a fairly complex version of that, where you're modeling the fundamental laws of fluid dynamics, like how fluids move and the conservation of mass. And you can use that with the initial conditions that represent a geometry of a tank, for example, and the positioning and of mechanical equipment and concentrations in your tank. You start with that, and then you let the mechanism unwind, and what you will see is just the transport of every the concentration of your chemical or your solids throughout that system at every point in space over time, just from the fundamentals. Empirical models are on the opposite end of that, where you don't actually rely on any physical mechanism or any mechanism at all. You just have, you have access to different values that you can measure, and then you put them in relation to each other. So here we have an example that comes to us from like the 1938, Mr. Greeley. So we've been doing that for a long time. What Mr. Greeley realized is that there's this equation here: removal of a substance is equal to the time spent in a tank divided by A plus B times T. A plus B, A and B don't mean anything. They're just parameters that are meaningless. However, that shape of an equation was fitting his data about BOD removal and suspended solids removal in tank reactors. So he could use that relationship, even though it didn't mean anything specific, to do predictions on what removal he could get. So there we go. And then a special class of those empirical models is machine learning. And there's so many types of machine learning models, right? There's tree-based methods, there's neural networks. If you push neural networks to their edge there, you get to something like a large language model, really deep learning. But what they are essentially is just models where not only is there no assumption about an underlying mechanism, there's also no assumption about the mathematical form that will describe the relationships you're trying to see. So you don't need to posit like a shape of equation, a division here, sum there. The model will find it itself. And you do that for two main classes of tasks: regression, where you try to map a numerical value to another numerical value, and classification, where you map certain numerical values to a label or to a category. So regression is good for soft sensors, influence generation, for instance. Classification is good for computer vision or fault detection, and many more. They can be extremely useful, and they have been, to detect patterns that are hard to see for our limited human minds, but they're really hard to interpret because they act more or less as a black box. You don't really see the mathematics of it, or you don't interact with it directly, and it's hard to narrate in words like mathematics can do usually. So there you go. That's a thing that exists. In between the first principles and the empirical is something we call semi-empirical, where we simplify mechanisms to an appropriate resolution, if you will. So for digestion of carbon in wastewater, I don't need to know about everything that goes on in a cell, even though I might have a model for that. Instead, I want to scale down, zoom out, and instead be like, okay, so there's different types of bacteria, and they consume different foods. And maybe that's enough for me. And I will use the tools of mathematics to describe how those high level processes work, but I'm not bogged down by the specifics of it. I'm inspired by them, but I'm not a slave to them. So we want to dive today a little bit more into details with those semi-empirical models, because we'll see a lot of those in the future. So a primer on activated sludge models is what we'll do. Activated sludge models, it's a family of models for biological wastewater treatment. My examples are from wastewater. I'm a wastewater guy. Apologies for all the non-wastewater people out there. But big picture, ASM models, they will model populations of bacteria, the fact that they grow and they decay, and the fact that they consume foods, they produce other chemicals that can be used as food by other things, and they breathe as well. So that's the main mechanisms. And they're super useful in the wastewater field to determine like how big reactors should be to get to a certain endpoint concentration, or estimate oxygen requirements, see how much sludge is produced per day, like these operational questions and design questions that are really important to us. If we take a little piece of ASM, the heterotrophic carbon removal. Heterotrophic just means it's done by heterotrophic organisms, so organisms that need external carbon. So we take that little piece of ASM, and what it tells us is that these organisms, they need two things to exist. They need a carbon source and they need oxygen. And they get those two things from the wastewater coming in, that's mostly the carbon, and then by supplied air. And they can only do two things once they get those things. They can either grow, make more of themselves, or they can die. That is all they do. There's also like production of carbon dioxide. We don't model that because that's not important to us. And we get to pick what's important to us. So the typical way of representing that type of system is through a mass balance. So a mass balance is expressing the amount of substance, how the amount of a substance inside a system changes over time. So you take all the things that might cause the mass to change, transport in and out, production of the thing, consumption of the thing, and you put them in the same equation. So the way it looks will be like that. The change of mass over time will be what comes in minus what comes out, plus the sum of however much of a thing is consumed by a process that goes on in the tank, times how quickly that thing happens, times the volume. And if you bring that back into concentration form, because that's helpful when we're in water, it looks like transport flux coming in and out, plus the sum of the coefficient of the process times the speed of the process. A stoichiometric coefficient, we'll look at what that means. So that is the substance view, right? You can do that dc dt equation for every substance of interest in your model. And you end up with those really big, like, differential equations that have lots of terms and they're a little bit hard to parse. And you see that some of the terms, like those that are in braces here, they tend to repeat in many equations. So it's there might be you might be thinking, is there a better way to represent this? And I'm glad you asked. So the one way to look at it is the process-based view, where you take all the process that happen in your reactor. So the growth process that we talked about, the decay process and the aeration process, and then you describe each of them based on the stoichiometry. So how much of every substance you need to produce the products of the process. And then you can think of that as the ingredients for your process, and then the rates, which is sort of the cooking time in your recipe, right? So you can describe them individually like that, put them in different places. And what you can start to do is lump together the coefficients that are in front of any given substance. So you keep the S's together, you keep the SO's together, you keep the XH's together, and then you can align them in a neat little table. And that is the Guyer matrix formulation for model definition. So the way it looks, again, is the processes on rows. You have the stoichiometric coefficients for every substance aligned together in those columns. And the way you would read that, that would allow you to express all of the transformations, production, consumption that happen in your reactor. So it would be the sum of the stoichiometric coefficients multiplied by the rates. So for S, it would be so ds dt, so the change of S in time would be this coefficient multiplied by this rate plus this coefficient times this rate plus this coefficient times this rate. And you repeat that for every substance, and you end up with your mass balance again. So that is just a very compact way to decode systems that can if they are in their equation form, get really unwieldy very fast. You will see Gruyere matrices if you stay tuned for our next MIA Academy webinar next month, I believe, about ASM. Going back to the surface, we can breathe. I'll leave you alone with math for today. So just to briefly sum up, because we've gone through those categories of models, we went through all kinds of mathematical models, and so why should you care? Why should you use them? Well, for all the same reasons that I said earlier, that you should use models at all, right? So you simplify things, you think in systems, you get people to agree or see the things in the same way as you. But on top of that, you end up with this really powerful tool of mathematics that allows you to generate new knowledge beyond what you put into the thing. Allows you to reuse a lot of pre-existing knowledge using like the mathematics of somebody else. You compress all of your expertise, all that data, all these assumptions into this one reusable artifact. And as you saw, there's so many categories of mathematical models. It's a really powerful approach, highly adaptable, highly flexible, and that is why you should care, in my opinion. So yeah, that is the end of my section. I thank you so much for your attention, and I will hand it over now to my co-host, Bruce Johnson.
Thanks, Jean-David. This great presentation on bringing together all the modeling stuff. So thank you for that. So my role is going to be one of how do you use all this stuff? I've been doing this, as mentioned, for 30 years. So I wanted to give everybody some context for that. So next slide. So, similar to Jean-David, I'm a wastewater guy, but I will say that these principles apply throughout the water profession. And not everyone realizes this, but over the last 20 years, the wastewater industry transitioned from primarily heuristic or rules of thumb, kilograms per cubic meter of volume, etc., to using and designing and developing models to help us do these things better than they had been in the past. Next slide. So why? What was the benefit of this? There has to be a value in that. Well, these simulators and models, they capture decades of experience and research in a tool that can be directly used by people all over the world. And so these result in lower cost science-based designs. One time I did a design of a facility, one using the rules of thumbs from a local regulatory agency, and another one where I used the standard modeling tools in there. And the modeling one came out to be about 1/3 the size of those rules of thumb in there. And so there's a real value in doing that as long as you trust those tools in there. The other thing that's really critical for me is that these tools provide a platform to capture and communicate knowledge. It's a common language that process engineers and managers and operators can use to both help understand what's going on, as well as capture that knowledge and then illustrate their ideas. And then, of course, you can use it as a training platform. So, you have a task that you want to do, try that. What happens if you turn up the mixed liquor recycle rate? It's a way of understanding and doing that in the system. Okay, next slide. So one example of this is the use of innovation. You know, we're all engineers and curious, and we have this great idea, this innovative idea out there that we want to use in here. And so the old school approach to this was, well, it's convince your boss it's worth investing some money in there. And so you design, build, and actually pilot this new technology at a real facility. You'd gain some experience with it, and then you'd say, okay, it's time to really put the money where the mouth is, and try and build a real plant based on that pilot. There was a lot of stress, a little bit of prayer to make hope that it actually worked in the full scale in there. Well, what we can now do is because of this decades of experience and knowledge that's built into these models, we can do one of those first principles models, kind of. Our ASMs are a combination of first principles and heuristic type things, but you can actually explore it and use that to understand it. And you can help manage the risk through appropriate fallback plans. You can use the model to understand how it might be in there. Build that full scale plant, hopefully with a little bit less risk than you did in the old school method, and cross your fingers in there. This picture is actually a picture of a plant that did the first full-scale use of a first greenfield full-scale use of mobile biofilm treatment in an activated sludge plant. And we did that based on modeling. There was no piloting that went at this specific site, and we managed the risk according to that. So this is, let's go one more slide here before I get into the next piece. Okay. And so this knowledge that we capture from that, it's a two-way street. So I can use the knowledge in the models to help design that facility. But once it's running and starting up, I can actually capture additional knowledge that we found out in that facility within the model to further expand and build on those systems in there. So this particular plant, I'll just explain to everyone what the problem was. This plant, what they had was the utility had a very small amount of money. They didn't have enough money to build the treatment that they needed at the plant. They had to hit some low phosphorus and ammonia numbers out of this facility in there, down to some pretty cold wastewater temperatures, down to, I think it was 8 degrees Celsius on the water temperature. And so, we proposed a kind of a conventional approach, and it was too expensive for them. We proposed a little bit more innovative approach where we use technology called IFAS, more well-established, lots of them in the industry. That was better, but they challenged us and said, we don't like all the plastic that's involved in IFAS systems. Everybody's worried about microplastics now. So then we said, well, there is this other new technology. We've been looking at it for a while. We actually developed a model of this technology. I was actually part of that model development in there. And we used kind of the first principles in the context of that system to evaluate this technology, then design and implement it. And that's what we ended up building. And fortunately, I still have a job, so the actual plant worked in there, and we moved on. So this is how we use, and I use models to help make our world a better place, basically. Next slide. So what I just described was actually consensus building. There's a lot of different people involved in the real world design and use of wastewater treatment or water treatment in there. And that common language of simulation provides the different parties the info they need to make these decisions. You've got process engineers, the folks who actually using it. You've got operations staff. They want to know how they're going to run the plant and why things happen in there. Managers, they're involved in wanting to understand the risk because they're spending a lot of money on something here, millions of dollars. And so they want to make sure that they're doing the right thing. Academia, what they do is they do a lot of tests and do a lot of sampling and come up with some weird things every now and then. But what they can do is they can actually build that into the model and check that the concepts align with all that experience in there. And then they can, once it's built into the models, that's a quick way to get out to practicing engineers like myself so that we can use it and get benefit out in the world. And then students, what does this equation really mean? You know, JD showed a neat little graphic in his PowerPoint about sliding the KS and mu max numbers in that model in there. And so that gives, you can use that math to actually understand how it impacts real world things in there. Next slide. Complexity. As which JD talked about earlier very well, the real world is complex, and understanding but you know, the good news is our understanding of how things works is also complex. The issue is no one can really hold all these complexities in their head, not in a real analytical way, only in kind of big generic things in there. And these models provide that way of capturing that known complexity and all those relationships and allows people who may not have a full understanding of the detailed differential equation that goes into modeling the growth of polyphosphate granules and PAOs, for example. But we have the trust and the knowledge to say that it's right in there. Now, this is both a blessing and a curse. You know, there's a favorite saying that I have, all models are wrong. I'm going to repeat that. All models are wrong. But some are useful in there. And you have to have the knowledge and to understand when they are too wrong. So it's very easy. And one of my most painful things is when some young engineer comes to me and says, oh, look, this model says X and Y. I said, oh, really? Interesting. Okay. What was the data? How'd you calibrate the model? Oh, I just used the defaults. No, it doesn't work that way. You've got to have the knowledge and make sure that you calibrate it so you don't fall into that trap of seeing too many decimal points coming out of these simulations. Next slide. So also, as Jean David brought up, you got to pick an appropriate level of complexities. And it's not only in the model selection, but how much time you spend on getting it right in the system. It's really easy for folks to dive in and spend a lot of time and money getting a model perfect. And you don't need that. You need to keep it just enough effort and just enough complexity to do what you need to do at hand. You know, keep it simple, stupid. You know, the KISS principle. Simulators are simply a tool to get to the appropriate answer. They're not the answer. It's important that that level of complexity is managed and you pick the right model for the situation. Next slide. So just briefly on career benefits, why do you care about this career? Well, I've made my career out of modeling. It's a place where you can learn how things work. It's how I learned the fundamentals of a lot of process engineering and how things work. I actually dove in to those Guyer matrices that was shown earlier and tried to understand why things happened in there. And when I mentor a young process engineer, I actually tell them, just dig in, find out, play with it, see what happens. When things don't make sense to you, find out why. It's just a good place to learn. And because of all that knowledge that's built in there, these aren't just equations. And I'll bluntly say that I myself, I don't hire folks that don't have at least some familiarity with the commercial simulators in there. And my consulting engineering firm that I work for, Jacobs, almost all process engineering at Jacobs has simulation at its base. We require that on all of our projects in there. It's the best way we have for doing quality control. Next slide. So the industry future. We all know the world is moving into a new digital age with machine learning and big science and data centers and all that stuff. There's a tendency in our industry to say machine learning will solve it all. But why would we want to throw away all the knowledge we've got built in these models? This stuff is not exclusive of each other. They can be complementary if you use it right in there. And so this efficient application and use of our collective experience is where the most value can be had in a career in there. And knowing how to do the simulation, both its strengths and its weaknesses, is a critical piece of understanding that I hope this MIA series will help everyone out and work through. And I think that's it for me. So I'll pass it back to see if there's any to Amr. Okay, good.
Thank you very much, Bruce and JD, for the great presentations and insights, and also a special thank you for Bruce for joining us at 3 a.m. in the morning. And now we'll open the floor for questions. If anyone has any questions, just please raise your hand, and we'll and then unmute yourself.
I guess if you're shy, you can also put questions in the chat.
Exactly. Or we can just assume you did a splendid job and nobody has anything.
Sorry, I do have a question. I'm a bit ill, so I'm sorry about my voice. I was wondering the MIA appointments, when or where will they be published? Because I just saw the LinkedIn post, but it was a bit unclear to see. Will it just be on LinkedIn, or is there a web page as well?
I think that's a question for Saba specifically, right?
Well, I can venture
Yep.
an answer maybe. Well, my understanding is there's a YouTube channel, right? So we will be having those webinars. We're publishing the announcements that there will be new webinars in mostly on LinkedIn, possibly is there a newsletter?
There's
LinkedIn and IWA Connect Plus.
Okay, IWA Connect Plus, like these professional social networks. That's where the
Okay.
announcements are. And then the YouTube channel is where the recordings will be published.
Okay, thank you very much.
And you'll be able to find the link to the YouTube channel on the MIA website if you're looking for that.
Great, thanks.
I saw there's a question in the chat, I think, for you.
Yeah, it's from Cheng.
Okay, quick from Chen Yang. Whoops. A quick question for JD about the definition of bad data. Can you share your opinion about if bad data still has value? Yes, I can. And then the answer is yes. Well, like everything, data quality is on a spectrum, right? And depending on what you're trying to do, a certain quality level might get you there or it might not. So a way in which data can be bad is, for instance, if you have a sensor and you don't maintain it, right? So then what will happen is some biofilm will grow on it, and at some point, say it's measuring DO, like the oxygen has to go through the biofilm, and it's not as accurate over time. There's drift happening and all kinds of things. Well, if you want to know the exact value of DO in your reactor, that will be too bad. It won't help you do that. It'll be hard to recover like the real signal out of just that sensor that was unmaintained. But if you're interested in like the dynamics of DO, how it moves up and down, and maybe you're trying to use that for some modeling, like some colleagues are doing, then that might be plenty. Same like if you're for some things, like if you're trying to like monitor really fast moving phenomena, like very rapid changes in your concentrations, and you have a sensor that just has a low resolution, like of samples every minute, it might be too bad to do the job. So it's all a matter of what the purpose is. And so I think all data should be kept raw and then like with a lot of context, and then people should process it according to their purpose and say what they did.
I'll
Another
just pile
question.
on
Yeah, if you
just a
can add on
little,
to
just a little bit, is that even bad data has useful information in it. So you've got to figure out how to take that and use that appropriately. But that's, as JD said, we should keep the data because there is useful information there. If it's really bad data, there might not be much, but there's still information.
Another question in the chat is how can you manage the data drift for sensors in order to create good models? I think we actually have a session on data handling, but I'll let both of you answer that if you have any insights on it.
I'll take the first cut at it.
Yeah.
So drift is a notoriously difficult thing to detect in sensors. Some of the modern machine learning tools can do that, but the current trend of starting to look at digital twins and putting that drift in context of the models actually starts to highlight when things can drift like that. For example, if you have a digital twin and the plant is doing this, and this in three different places, and one of these doesn't make any sense, that is a way of detecting that drift. This concept is one JD mentioned in quickly of one of a soft sensor, where you have that model of the plant that you can estimate what must be going on at places based on all the other data around it. And so that is a concept that can be applied using some of these more sophisticated model-based control and simulation approaches.
JD, anything to add?
Not really, but I think um, that covers and extends what I know. Except one thing I can think of, for managing drift is like redundancy. But then again, two sensors can drift in different ways, or at least at the same time. So that's not a foolproof thing. And yeah, like getting at the root of the thing, if you can, like if you have control over how the sensors are being maintained, like making sure that the cleaning frequency and so on and the calibration fits the level of quality or of consistency that you're looking for. But of course, that's not always possible.
Another question for Bruce. When you mentioned digitalization, you feel like the industry is shifting quickly towards machine learning and digital twins and giving less trust or attention to mechanistic models, or maybe mechanistic models have not yet reached enough of the industry and became standard.
Wow. wow, I could talk an hour about that subject. Yes, the industry is shifting and starting to be more accepting of some of these more advanced digital tools in there. Machine learning is one of them, and there are one of the pitfalls of machine learning is that any good computer folk can implement machine learning and not have a lot of domain knowledge, i.e., knowledge of the water industry in there. And there's a lot of that out there, and there's a lot of hype around that. I'd be careful about lumping digital twins, though, in that, because digital twins are not necessarily machine learning based and digital in there. They can be purely mechanistic, as you say in there, or they can be hybrid, where you combine the benefits of both these new digital tools with machine learning and the mechanistic models together. Iowa and the MIA group has been pushing a little bit more toward the hybrid side, where we take the benefits of both because they both have advantages and disadvantages with them. We're avid fans of all the knowledge that we have built into the models over the decades in there, and we don't want to throw that away, and nor do we think it would be appropriate to do so. And the mechanistic models are actually the more mature piece of it. They are the standard for design right now across the world, I believe.
I think this other question is also for Bruce. Are modeling tools still the most commonly used for design of wastewater treatment plants, or is their complexity still prohibitive for the daily management of plants?
Wow, another one I could go into, dive in and never come up on. Yes, wastewater tools are very commonly used, and in fact, mostly the standard for designing wastewater treatment plants nowadays. This is a relatively recent change in our industry, though I mentioned probably in the last 10 to 20 years, this is when this transition has happened in there. The complexity still prohibitive for daily management of the plants. These models do take a skill set, and so they haven't been widely adopted in day-to-day operation of facilities because of the complexity and the skills it takes to do that. But with the advent of some of these digital tools and automation and machine learning, that is actually changing right now, where the things like digital twins, I believe, are being brought to bear in a way that is usable at wastewater plants in managing and understanding them in there.
So we have another question. Someone is actually particularly interested in learning more about simulation software currently being used in firms to model growth processes and hydraulic aspects like physical, chemical, biological processes, hydraulic simulation and flow dynamics, anaerobic digestion modeling of biogas production. I think every process simulator has all of that right now, but if you want to add a bit more to that, maybe you can tell us, JD and Ambrose, if you've dealt with anything specifically.
Well, I mean, we there's a lot of commercial simulators out there. I won't list them off in fairness because I'll probably forget one in there. And as Amber said, they're all out there. There's a lot of publications. I'd start with all the IWA publications on this. I'd also recommend, if you're looking at it more from a practice aspect, the Water Environment Federation has some more practice-oriented manuals of practice related to modeling and the use of models in the design and operation of plants. So there's a lot of resources out there for you to dig into that.
Yeah. Another question is, considering how difficult it is to calibrate mechanistic models, are they still used when a plant has enough data to run a machine learning model? Are hybrid models useful, or will the deterministic ones be dropped once enough data is collected for machine learning to run reliably?
I've got some strong opinions about that, and I'll let JD
By
talk.
all means.
Yes, machine learning models. Wastewater plants are inherently chaotic, both in the data and the variability in the parameters in there. And there is no practical way, at least I would consider the next 20 years, to train a machine learning model all on its own to capture everything that can go on a facility and all the interactions and what happens if the headwork screen goes off to the dewatering press down at the end of the plant as it goes through there. I think mechanistic models will always have that role in there. And if for no other reason, it lets us figure out why. And that's really important to a lot of people. Unfortunately, some don't care about why sometimes and just want to get out of the way. But I think we're better than that as an industry, and there's a lot of value in there. I'm running a hybrid digital twin of 3 or 4 different facilities right now live. So yes, they work.
For practical applications, what would you consider an acceptable level of model efficiency for machine learning models or any model in general to be reliable, applicable in operations?
The Good Modeling Practice book that IWA put out actually has some recommendations around model accuracy for the results in there. That's a great book to look at to understand this overall system in there. That ranges from dead on accurate up to 20-30% off. Yeah, off. And that only applies to the parameters you care about.
And also, we have a session on model calibration, validation, and evaluation. So maybe if you come to that session, that question will be answered to a greater level of detail. But these are all the questions in the chat. If anyone wants to has any other question, you're welcome to put it. We still have about 7 minutes, so you can either speak up or put the question in the chat. But if there's no questions,
IWA's Good Modeling Practice. It's
called Guidelines for Activated Sludge Models, I think.
Oh, okay. I don't know if it was a GMP. It's a scientific and technical report within IWA.
I might have a point to add to a preceding question, like the one about so will basically machine learning models replace mechanistic ones? Everything that Bruce said, like, it was I think on point. The thing I want to like emphasize and not necessarily add because it was mentioned before is that the mechanistic models and their mathematical form, they're not only modeling tool, they're a language. They allow people to discuss what is going on in the plant and how things, like what mechanisms are at play and so on. And if you go towards the fully machine learning approach, maybe you still get good results, but you deprive yourself of that ability to talk about it. And that might be critical depending on what you're trying to do. If you're trying to convince management to do this and that, like then you need the words to convince them. These tools probably go hand in hand. And also, I want to open a door to like maybe the not so far off future where maybe the machine learning component is not so much like being this black box that maps inputs to outputs, but rather is an agent that takes care of calibrating the model for you, right? So now with these large language models and these like more advanced AI systems that are autonomous, you can sort of automate a lot of the grunt work. Of course, key is staying critical and always overseeing, but there's this way that maybe those machine learning approaches can be allies in ways that we haven't been thinking of in the recent past. So something maybe exciting to think about.
Thank you very much. Yeah.
Okay. So if there's no more questions, I would first like to thank our speakers, Bruce and Jean-David, for a very nice explanation on what are models and why are they useful. And then to end this session, I just want to send out a reminder that our next session is about activated sludge models. The date will be announced very soon. It will probably be around the end of November, and the speakers will also be announced. And this session will just explain the basic theory and concepts of activated sludge models. So thank you everyone for joining, and enjoy the rest of your day.
Thank you.
Thanks, everyone.
Thank you, everyone.